Okay, continuing on with orthogonal sets. Okay, we have what are referred to as orthonormal sets, and this is sort of melding together what we have with orthogonal and unit vectors. And so we have with an orthonormal set, we have by definition an orthogonal set of unit vectors. And we have just as this quick example, it says to determine if the following set of vectors is orthogonal, and if it is only orthogonal, normalize the vectors to produce an orthonormal set. Okay, so we have three vectors. Okay, v of 1, v of 2, and v of 3. Okay, we have the first vector, we have 1/2, 3/4, and 3/4. Second, we have 3 halves, -1/2 and -1/2. And the third vector, we have 0, -1, and 1. And again, the set will be orthogonal if all the dot product combinations will equal to 0. So we have for the dot product between first two vectors, that will come out to 0. Dot product between v of 1 and v of 3, also at 0. And if I took the dot product between the second and third vectors, you also have to be 0. So you have 0 to be the result for all the dot product combinations. And so this set is going to be orthogonal. Now, to see if the set is going to be orthonormal, okay, each of the vectors, all the vectors must be unit vectors. And it turns out that for the first vector, okay, it's going to turn out that for the dot product, okay, you have square of 1/2, square of 3/4, square of 3/4. So this would be 22/16. And so since this is not equal to 1, now the set is not yet going to be orthonormal. Okay, so as part of the remedy, okay, so the length of the first vector, okay, in exact terms will be the square root of 22/4. So I'm taking the square root of the dot product between the first vector and itself, and so we have the square root of 22/4. Likewise, we have with the second vector, okay, now the dot product between that and itself comes out to 11/4. Okay, so we don't have a unit vector yet, but we're going to convert it as such in a moment. So we have with the magnitude of the second vector, again, we have what's going to be the square root of 11/4, and that is reducible to the square root of 11/2. And for the third vector, also not a unit vector, and we will remedy that shortly. So we have taken the magnitude, okay, this comes out to the square root of 2. And so normalizing the vectors, okay, so making what we have for v of 1, v of 2, and v of 3, converting those and translating in terms of a unit vector. So we have for the first vector, okay, making this into a unit vector, we have v of 1 divided by the magnitude. Again, we had v of 1 consisting of 1/2, 3/4, and 3/4, and the magnitude is the square root of 22/4, and dividing by this ratio or multiplying by the reciprocal, normalizing. Okay, so v of 1 becomes u of 1, which should be 2 over the square root of 22, 3 over the square root of 22, and 3 over the square root of 22. And for the second vector, again, the magnitude was the square root of 11/2, and multiplying the elements of what we have in the second vector by the reciprocal, that is by 2 over the square root of 11. We have for this normalized second vector, we had the unit vector, whereupon we have 3 over the square root of 11, and -1 over the square root of 11, -1 over the square root of 11. And we have for the third vector, normalizing this, we have the elements and dividing by the magnitude, which was the square root of 2. And the result here, we have 0, -1 over the square root of 2, and +1 over the square root of 2. And do not worry about rationalizing the denominator. So this would be the normalized set here, and they would still be orthogonal. And since all these vectors have been converted to unit vectors, we have these three sets, u of 1, u of 2, and u of 3, to be regarded as orthonormal.